Hello, welcome to Realize Live in this session on Simcenter FLOEFD for Solid Edge. We're going to be taking a look at how to create fast, accurate, and easy fluid flow analysis for the design engineer. My name is Ben Weisenberger. I'm an application engineer, part of the Global Technical Enablement Group for Solid Edge. I'm joined today by Matthew Fresco, the director of WashTech. We'll be using one of their assemblies to do our analysis today. Matthew?
Hello everyone, I'm Matthew Fresco. I'm the managing director of WashTech. We have a production facility in Querétaro, central Mexico, and we're soon to inaugurate a new office in Dallas, Texas. We basically do washing and cleaning system for the aerospace, the automotive industry, and some other industries like optical, medical, and things like that. The solid edge solution is actually quite nice for us. It makes us save a lot of time, and we can get a quote and get ready to manufacture in a very short period of time.
All right, thank you for that. And let's go ahead and jump right in. In this example, we're going to show you one of the core operations of this machine tool cleaning machine by WashTech. Now the machine has multiple applications ranging from the pump down here, the filtration systems, ducting systems, valves, and ventilation. But the core application here is the cleaning chamber, where the part is placed onto the machine and either sprayed with a cleaning solution or dried with high velocity air. To view this, we're going to switch to a smaller assembly. Now in this model we can see this is the simplified cleaning chamber, and inside of the chamber we can see the fixture on which the machine part is placed. We also see the arms that direct the airflow onto the main part to dry it. If we look at the model in a section view, we can see that we have an inlet here at the top where the air comes in. The air branches off to both arms and then exits the nozzles and blows air onto the part in the middle of the chamber. On the bottom of the cylinder, we can see we have the outlet where the air leaves the chamber. Now in order to analyze this, we need to make sure that the geometry is clean and that there are no issues or with wrong parts or bad connections. So we can do that by simply analyzing the internal flow and showing the internal volume. The geometry will be scanned, and if it can recognize a fluid volume, it will display it as we see here. Any problems with the geometry would be highlighted at the bottom of the screen, therefore making it easy to find and correct. Now, since the geometry is clean of any errors, we can start setting up the project. In order to do that, we'll run through the wizard, which guides us through the basic steps. Now we can start by specifying the project name, such as drying. We can then hit next, and for our units we can change the temperature, in this case from Kelvin to Celsius, and the pressure from Pascal to bar. In loads and motion, we will change the volume flow rate to liter per minute. In the next step, we must select what physics the simulation should consider. And in our case, it's an internal simulation because we're only going to analyze inside the rotating geometry. We have no heat conduction, radiation, time dependency, gravity, rotation, or free surface sloshing. Only the air flowing into the chamber, so we can skip all of those settings. Next, we have to select our fluid, which is air in this case. We can then skip the next step and finally specify the air temperature that we want to analyze. We'll leave that at the default setting in this example. The computational domain is automatically generated by the geometry that was recognized, which we can go ahead and hide. Now we have to specify the inlet, which we'll do with a boundary condition. We'll choose the inlet lid and define it with a total pressure of 5 bar. We're also going to use a flow rate goal defined directly in the boundary condition. We can rename the boundary condition to 5 bar so that it's easy to recognize. We also need a boundary condition for the outlet, so we can select the outlet surface, which is in contact with the fluid volume. We'll define a static boundary pressure condition with 1 bar of pressure. We'll also rename this condition to 1 bar. In addition to the flow rate goal, we may be interested in other goals such as velocities for the overall simulation. To do that, we'll create some global goals next. Here we'll use static pressure as well as velocity for the global simulation. If we specify a surface goal on the inlet for the total pressure, we'll simply get the same value as the boundary goal. So instead, we'll look to get a value for the total pressure at the outlet and rename the goal to outlet. Since the fluid is traveling through a lot of nozzles, we would have a high pressure drop between the inlet and outlet, and we can calculate it directly with an equation goal. The definition of a global goal is basically the total pressure at the inlet, which we can select from the boundary condition and add that with the plus button, minus the surface goal of total pressure at the outlet. So I have a pressure boundary condition, and we can go ahead and rename that to delta PT for pressure total. Now the geometry is already defined and the boundary conditions are good, but because of the small nozzle openings in the thin arm material, we need a finer mesh. The easiest way to do this is with the automatic mesh refinement. If we go into the calculation control options and select the refinement tab, we can specify global level 1 or 2 and select tabular refinement with travels being defined. If we specify the table and add 2 rows, we can enter in values of 0.7 and 0.9 travels. So these values are just before 1 travel. After 1 travel, FLOEFD starts comparing the convergent, and so this way we get a mesh refinement just before it starts looking at the convergence of the goals. This is now set, so we can click OK. We are now ready to run, and the mesh adjustment will happen during the solve automatically. Since we're ready now, we can run the simulation. Automatic meshing and solving happens after each other, so we can go ahead and click Run. We will get our solver monitor, where we can see the models getting compared. The mesh is starting, and we can see the initial mesh is around 38,000 cells. Now the first goal is already popping up, and we can see that we have a delta PT of around 4 bar. We can also see that our velocity is starting to increase. If we want to, we can create a plot in the right section plane to visualize the velocity. Here we can see how the velocity is developing inside of the arm and throughout the nozzles. If we right-click on the pictures and select Properties, we can add in options to display the mesh to see what it looks like at this moment. Once we reach our 0.7 travels here, we will refine the mesh, and we can take a look afterwards to see where it was refined and what it looks like. The mesh refinement will start now, and we can see it preparing the model and mesh capturing, and the mesh size changes from 38,000 to now 94,000 cells. Once the picture updates, we can see that the mesh size automatically adjusts to the model. After a few more iterations, and once we reach 0.9 travels, another meshing iteration will happen and the mesh will refine again. Here we can see it preparing the model once again, capturing the mesh and changing the mesh size from 94,000 all the way up to 160,000 cells. And the plot will be updated in a moment. Here we can see a much finer plot. Now it'll take more time for the goals to converge, so we'll skip ahead and go ahead and view the results. Now after a total simulation time of around 9 minutes, we can see our goals have converged. We've reached a steady state, and we can see that our flow now looks like this. We can look into more detail of the simulation by going back to Solid Edge in Simcenter FLOEFD. Here we can use cut plots, for example, to show the velocity. We can see flow vortices very nicely in the middle, as well as how the flow branches off to both arms and the high velocity peaks at the nozzle exits. We can also visualize the pressure and see where the highest pressure drops are, such as in the T-junction up at the top. Another plot we can view is the flow distribution to see how equally the flow is distributed between the nozzle openings. To make this easier to see, we can use the surface parameters that can show the mass flow rates for each of the nozzles. We can see that they are all roughly about the same and have a relatively good equal distribution. If we show a surface plot of the velocity onto the machine part, we can see that there are some hot spots where the velocity is very high on the component. If we visualize some of the trajectories, we can see that the air flowing from this nozzle is blowing exactly on the high velocity area of the surface plot. We can also visualize the overall trajectories in the model. Here we are displaying arrows which we can animate to show how the air is moving. If we want to show some of the velocities at the nozzles, we can specify isosurface velocities for the values of 20 to 30 meters per second. So this is how we can use Simcenter FLOEFD to analyze our models inside of Solid Edge.